loud. All right. All right. Hi, everyone. So today is going to be, well, we're going to dive into induction. So, or as I put it here, induction. It's a very exciting topic. It's sort of one of the classic topics when you sort of learn how to write proofs. I don't think I need the screen for quite a while, so let's get rid of it. Okay, so let's just kind of dive in, because we sort of did contradiction proofs on last Thursday, right? And now that's one of the big styles of proof. Another big style of proof is induction proofs. And so let's just kind of dive into it with an example. And actually, it's something that I think we saw when we were looking at those patterns and sets. There was like that handout we were looking at. There was a problem that ended up being one. It ended up being squares plus one, but most of you were noticing that the differences were odds, or consecutive odd numbers. And so here's a general proposition. The sum of the first n odd numbers is n squared, right? For example, 1 plus 3 is 4, which is 2 squared. 1 plus 3 plus 5 is 9, which is 3 squared. 1 plus 3 plus 5 plus 7 is 16, you can check, which is 4 squared, etc., right? So, well, that worked for the first few examples. Doesn't mean it's going to work forever, but but we might suspect there's a pattern, and I'm actually telling you that there is. I'll show you at some point examples where like there's a pattern that seems to be a pattern, but then it breaks down. There's some interesting places in math where like something looks like a pattern, but it turns out not to be. Remind me to tell you that at some point, just because there's at least one nice one I can think of, like I've thought about off the top of my head. But the real question is, how would we prove this for general n? Right, because I don't know, it's a little bit, if I wanted to somehow prove that some of the first 1,000 odd numbers was 1,000 squared or something, it's not clear, right? I mean, you can check cases, but there is a picture proof that's pretty compelling. I just sneezed into my mask. It's always, I want to take my mask down to sneeze. That seems wrong, but now that seems kind of okay. Luckily, it wasn't too snotty. All right, there is a picture proof that I kind of like, and it's insightful. It brings insight. But okay, that represents 1. Here's a way I can represent 3. So there's 1. There's 3. Here's how I can represent 5. Yeah, you see where I'm going with this? Kind of nice, huh? Definitely this is like an insight, Right, so this is a proof, that 1 plus 3 plus 5 plus 7 equals 4 squared, right? That you sort of break each, you can sort of see that like you can break the odds into these little L-shaped pieces, right? And that's nice, that's great. And in fact, that is insightful, and I think I really like that proof, or quote unquote proof, because it's not really a full proof, it's more like a picture. But and because we're trying to be rigorous in this class, right? So like, how are you going to actually show, like, does this really prove it for like the case for the first 100? odds, you could sort of, I think convince yourself that the pattern will continue. But it's not the same thing as like a rigorous proof that's a general, argument. So this proves the case n equals 4, and is certainly insightful as to why it might be true in general. But it does not constitute a rigorous proof. And the thing about induction is it will let us do a rigorous proof of this. One thing I will say about induction, though, is that it's actually rarely insightful. It's sort of a little bit of a mechanical thing. I mean, it provides some insight, I guess, but it's like, this to me is the reason why the sum of the first in odd numbers is n squared, right? Like this feels like the reason. But so how to do this? So I'm still asking this question: how do we prove this for general n? I guess sorry, this doesn't constitute rigorous proof for all n. Okay, so let's look at I do want to look at an example. Like, how could we prove? Well, the idea of induction, you might have heard of it before. There's a metaphor of this. It's like, suppose there's like an infinite ladder that you want to climb. Okay. And there's like rules for how do you climb a ladder, right? So, and I want to be able to say that I could climb as far up the ladder as possible. So there's two pieces of information you need to be able to do this. What's the first? Anybody tell me what I have to do to be able to climb a ladder? This is such a vague, random question. Just curious to see what your thoughts are. Yeah. You have to be able to get on the ladder. Very important. You have to get on the ladder. That's the first step, right? I have to be able to grab on ladder and get on somewhere and run around. Okay, so that's the first step. And then here's a way you could argue that I could climb as far as I want, which is that if I'm on a rung, I can climb to the next rung. If you believe that that's possible, then sort of logically, I can keep climbing one more. Once I'm on the ladder and once I can know I can climb from one rung to the next, then I can climb forever. And that's basically the idea of induction. So, induction. So we need induction to prove something like this. Sort of, yeah, let me just write that down. What we said, infinite ladder, metaphor, ladder. Metaphor. To climb forever. One, have to get on the ladder, have to be able to get on the ladder somewhere. And two, have to know that if we are at a rung, we can climb to the next rung. We are at one rung, we can climb to the next. So this is kind of the way people think about induction, is that if you want to prove something's true for all integers, you want to have some starting case. And we've already looked at some of the small cases, right? And then we want to prove that if we know it's true, like for case 50, then we know it's true for case 51. If we know it's true for case 100, then we know it's true for case 101. If we know it's true, so if we know it's true for case k, then we know it's true for case k plus 1. That's the idea. So let me write this down. So more formally, this is actually called weak induction. We'll talk about strong induction at a certain point, but so suppose we want to prove a statement P of n, I'm going to call it P of n because it's going to depend on n, is true for all n greater than some initial n, greater than or equal to n naught, some n naught in the integers. And I should say n is also in the integers. So this is about step by step. So this is not about like real numbers or anything. This is also an integer, right? Okay, right. So for our example up there is like that the sum of the first, our P of n would be the sum of the first n odd numbers is n squared. This could be an example of a P of n right here. All right, it's a mathematical statement, but it depends on n. So that's why we write P of n instead of just P. Okay, show P of n naught is true. So the initial case, it's called the base case. That's the first thing we have to show. So that's the whole getting on the ladder part of the metaphor, right? And then we have to show that if P of k is true, implies P of k plus 1 is true. Now, some books use n here. P of n is true implies P of n plus 1 is true. For some reason, I like to use a different letter, like, because this is supposed to be a generic n. When we prove it, we're going to pick a specific n, namely n equals k, and prove it's true for k plus 1 also. Then yes, P of n is true for all. That's what then induction says that. Oh, by the way, sorry, this is called the base case. And then this is called the inductive step. You know, it really is inductive reasoning. It's like the sun rose today, so we think it's going to rise tomorrow. That will not be true at some point. Yeah. Yep, k could be in not, right. That's right. So that's actually a good point. Like, if k happened to be n naught, then that would, and we prove this, that means we get it true for n naught plus 1. So that's the first step, like, right? And then we start working our way up from there. So then P of n is true for all n. I mean, I know I wrote that up there, but I just want to say this is kind of the statement of induction right here. Okay, so that's the kind of formal statement of induction. Right. And I want to do it for this example. Even for this example, I mean, I'll do a general case, but I do want to do still like a specific case just to illustrate the point. Like, in our example, suppose we know P of 50 is true. Right? i.e., I think the first 50 odd numbers goes up to 99 probably. Am I counting that correctly? Is that the first 50 odd numbers? 1 through 5, 7, 9 is the first 5. So yeah, I think that's right. Suppose we know this, like we know this statement right here, like we're given this. How can we show P of 51 is true? Okay, so I'm just trying to illustrate this before we do the general proof. You can kind of use that picture for some insight here. Right? So I want to put a plus 101 here and make this 51 squared, right? Now there's a couple ways to go about this. But maybe let's try to use that picture for insight. So, you know, let's consider that sum of the first 1 plus 3 plus 5 plus 95 plus 97 plus 99 plus 101. Okay. Because that's the first 51 odd numbers. I can assume this is true, so I can use it, right? Do you guys see what I want to do? Yeah, what do I want to do next? Yeah. Go ahead, please. Yeah, we're assuming this is true, and we're trying to show that this is 51 squared. So how can I use this here? What can I say this is equal to? Yeah. Yeah, right. We know this right here can be replaced with this. So this is 50 squared plus 101. Now the question is that, I mean, so you could check that that's 51 squared, but I don't want to do any arithmetic. I want to do like something general, right? Yeah. Yeah. The last number plus one. Like you're looking at the picture? So what does that give you? So I want to take that 101 and make it look like this somehow. You're counting this twice? I see what you're doing, but maybe it would be a little better to break it up like this, this, and this, and this. Is that what could that work also? Or maybe, I don't know, sorry. I'm just... Well, I was just thinking in terms of like the width and height of the box. Uh-huh. Those are two dimensions. We know that one of those sides, those have to equal your number added to that. Because sorry, no, I'm probably being dense and not following. Like this is 51, which you said was 101 plus 1 all over 2. Is that what you're saying? Yeah. Okay. So you have to add the two 51s together. And then you have an extra 1 that's been. Yeah, but you have an extra 1 because when you're wrapping it around, one of the width and height. The one is sort of extra. You need that extra 1. Yeah. So. You get, where are you going? I think I get what you're saying, but I would be yeah, I think just along very similar ways to what you're saying is you can think of this as like, I'm now thinking of this as like 50 by 50 this square. This is 51, you know. I think similarly, maybe not to have to do the double counting thing, you could break this into 50 plus 1. And then why is this going to actually work? So I almost started with 51 squared because I think that's actually maybe, you know, you're trying to prove an equality. So you can prove from one left to right or right to left, like left equals right or right equals left. And I don't know, when I wrote it down in my notes, I actually started with 51 squared. Maybe it's easier. But if you just think like algebraically, I could think of this as like 50 squared plus 2 50s plus 1. And if you start thinking like algebra, does this look like something? Something squared plus 2 times something plus 1. What is that the same as? Quantity squared. Yeah, so this is actually 50 plus 1 quantity squared because that's really what you get when you FOIL out 50 plus 1, right? You actually get 50 squared plus 50 plus 1. Yeah, maybe it's almost better to do it right to left or something. Like, I mean, from here up, that might actually be a better argument, like a more natural argument, is to take 51 squared, write it as 50 plus 1 quantity squared, FOIL it, recognize that this stuff that's left over is 101. You have 50 squared plus 101, so then you can replace 50 squared with this sum and get the whole sum. Maybe that's more natural. I don't know. I sort of decided on the fly to do it the other way. Whichever way, as long as you can start with one side of the inequality and prove the other, then you're fine, you know. So that actually does work. And we noticed we didn't actually add, I mean, yeah, we really didn't do any additions at all except sort of like foiling. And I guess we broke 101 into 250s plus 1. Or going this way, we took 250s plus 1 and combined them into 101. Does that make sense? Okay, so that's kind of general. I mean, that's a specific example. And we like didn't use it, we didn't really add anything ever. We didn't really add up the first 50 odds. We just used the fact that we're assuming that's true. Let's do the general case, I think, makes it more clear. So if we really wanted to prove this claim that I'm erasing, let me just actually write the proof. So proof. So let me rewrite it this way. So the proposition is that the sum from I equals 1 to n of 2i minus 1, that's a way to express the sum of the first n odd numbers. Because when I plug in 1, I get 2 times 1 minus 1, which is 1, right? So this is really maybe a little more formal way to say it. And then, so the proof is, we would say, by induction on n. Again, also you could, well, okay, so let's just actually call this P of n. Sometimes I don't refer to the P of n explicitly. Sometimes I just say, well, it's true for n equals 1. And then it's true, if it's true for n equals k, it's true for n equals k plus 1. And then just say it that way. So base case, by the way, I should say this is true for all n greater than or equal to 1. Right? I should have said that. So actually P of n does not include that part. Sorry. That's the P of n is the statement with the, because that's a specific, you know, statement, and then it's true for all n. Right, okay, so the base case, you can also do some base cases if you want to check. So n equals 1, P of 1 is that basically 1 equals 1 squared. P of 2, 1 plus 3 equals 2 squared. So, you know, we proved a couple of base cases. It's good to check a few. I'll show you some proofs where like, I'll show you some false proofs where like the n equals 1 works, but the n equals 2 doesn't, or something. And so it actually like doesn't really work. Or no, not, or maybe like, or no, sorry, I'll show you a proof for like, yeah, I'll show you a proof for a base case breaks down, but I'll also show you a proof for like the implication breaks down, the inductive step breaks down for like going from 1 to 2 or from 2 to 3 or something. So it's like for small cases, you have to be careful. So it can be good to check some things. Okay, so inductive step. Assume P of k is true. So the sum I equals 1 to k of 2i minus 1 equals k squared. I could write this as, I'm just using summation notation because that's also a little more rigorous than using like dot, dot, dot. Right. The dot, dot, dot's also something that we think of as sort of like a little bit unrigorous because like maybe something weird happens in the dot, 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 but when you put in summation notation, that's a little more. But you know, for ease of reading, maybe it's better to think of it this way. So consider, so let's consider, so we want to show, by the way, there's something I don't do as much, but a lot of people do, which is like they write like WTS for want to show. I noticed you did that when we were talking. So I feel like Professor Tabak also teaches this class as a big WTS person. So we want to show that the sum from I equals 1 to k plus 1 of 2i minus 1 equals k plus 1 squared. I'll put a question mark over that just to, again, we haven't established that yet. That's what we want to show. Okay. So now we can basically do this same argument, but for a general, and in fact, it'll probably be more compelling for like a general k. And like I said, I don't always refer to the p explicitly, so I would write something like assume true for n equals k. And then we want to show that it's true for n equals k plus 1. But if you think about it, this really is p of k plus 1, right? Okay, I'm belaboring this too much probably. All right, so again, what I would say is like just start with one side or the other and try to get to the other side because it's going to be FOIL. FOIL is going to be the main idea here, right? So yeah, we can write the sum I equals 1 to k plus 1, 2i minus 1. Right, this is, let me just do this again. This is 1 plus, I mean, I guess the question is, what's the last term now, actually? What's the last term going to be? What's the next term after 2k minus 1? 2k plus 1, right? So that's going to be 2k plus 1. And just I'm going to do it both ways. So you could do something like this. You could say something like this is I equals 1 to k, 2i minus 1, plus what you get when you plug in k plus 1, right? So if you just want to check that it's actually going to be the right thing. Yeah, like, because that's 2k plus 2 minus 1, which is 2k plus 1. And you could also write that as 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 plus 2k plus 1. I'm sort of saying you can do it either way. I'm just sort of like writing it both ways, both in summation notation and without. And then we know this equals k squared, right? So this equals k squared plus 2k plus 1 by the inductive assumption. And the same thing here. We could also write k squared for this part plus 2k plus 1. The inductive assumption. And now really you can see the FOIL thing, right? That this really is going to collapse as k plus 1 quantity squared equals k plus 1 quantity squared. That's exactly what we wanted to show. We wanted to show, therefore, p of k plus 1 is true. Or it's true for n equals k plus 1, however you want to write it. Okay, and so by induction, like if that's induction up there, then by induction it is true for all n. By induction, because we did the base case, we did the inductive step. By induction, p of n is true for all n greater than 1. Yeah, and that's the end of the proof. Okay. So it devolves to formal nonsense at some point a little bit, but you have to get good at that. Another thing I'll say that I see in books and some books and not is that like sometimes if I just assert p of n, I'm assuming it's true. Some people will just write by induction p of n for all n greater than 1. Like you could almost take away all these is trues, but I don't know. It's more readable to me to write is true. I'll develop your own style. You're becoming mathematical novelists. You know, you're going to be developing your own writing style. Okay, any questions about that? Or if I beat a dead horse and it's off instantly. Okay. I want to do one more example together as a class, and then I actually just want to give you guys some stuff to do in groups. try to do some of these on your own. Figure out what's going on. Okay, so here's another example. And this is a good one that's not true. It's not really true for n equals 1, 2, or 3. It starts at n equals 4, so it starts a little differently. All right. Let's do another induction proof. Just to see if we can get the hang of this. So proposition. For all n greater than or equal to 4, I want to compare n factorial to 2 to the n. Yeah, right. Is that true? Is it true for 4? Is it true for 3? Yeah, 3 factorial is 6, right? So it's kind of nice. It's not really true for actually for 1, 2, or 3, but it's true starting from 4 on. Does it feel true? I mean, how do you have a good feel for factorial growth? Factorials grow quickly, right? And again, there's some issue of like feeling this is true. This is multiplying the number 2 together n times. But this is multiplying numbers 1 through n together, which is another product of n numbers, but they get the numbers that you're multiplying get larger and larger. So it should, besides just proving doing the formal induction proof, you should try to convince yourself. And actually, that's going to be part of the proof, really, is that feeling. So, proof. Again, we can sort of say this is our P of n statement right here. By induction on n, I write this because things can get hairy. You can have more variables floating along. There's some double induction proofs where it's like you have some statement about something that's m and n, and you prove it first. You first induct on m, then you induct on n. You can get really hairy and unpleasant with this stuff. But I'm just gonna, I like to say, by induction on n. Base case. So now the base case is n equals 4, right? We could check 5 also if we wanted to, but yeah, so 4 factorial is 24, is greater than 2 to the 4th, which is 16. Check. Right? Base case is always the nice part of the proof. Pretty straightforward. Now, assume it's true. Oh, sorry. Inductive step. So assume true for n equals k, i.e. that k factorial is greater than 2 to the k. So this is our going from one rung to the next thing. So we want to show that k plus 1 factorial is greater than 2 to the k plus 1, right? All right, so how can we do this? How can we start to bring in the inductive assumption? Yeah. Right, so this we could think of as 2 to the k times 2. This we could think of as k plus 1 times k factorial. Good, I do want to go from one side to another because I want to prove this. So I don't want to just use this statement. So I'll just do one or the other. So let's start with, like you said, k plus 1 factorial. The nice thing about factorials is that's that same thing as k plus 1 times k factorial, right? And then what can I say next? Once I have the k factorial there. Yeah. I see what you're saying. You want to sort of do it. Yeah, okay, let's do it that way. I was going to do it as a chain of inequalities, but I kind of like your way too. Like, so you want to use something that if like, you basically want to use something that like if A is greater than B and C is greater than D, then AC is greater than BD. Is kind of what you're trying to use there. Okay, so you're saying K factorial is greater than 2 to the K, and K plus 1 is greater than 2, since K is greater than or equal to 4. So these two together imply that K factorial times K plus 1 is greater than 2 to the K times 2. But the left-hand side is K plus 1 factorial, and the right-hand side is 2 to the K plus 1. Good, I like that. Yeah, I don't know why this is the way I think about it, but I think I just, let me see, is this, part of this board is on the video. So I think I was just gonna say like, okay, well, you could say K plus 1 factorial equals K plus 1 times K factorial. That's greater than K plus 1 times 2 to the K. No, not K squared, K factorial, sorry. The inductive assumption I can use right here, right? Since K factorial is greater than 2 to the K, I can make that a greater than. And the fact that this is greater than 2 means that's greater than 2 times 2 to the K, which is 2 to the K plus 1. But in some ways, that's kind of contrived. I like the way. I don't know. Again, I think I said this in the email about my solutions. Like, my solutions aren't the solutions. They are solutions, but there's obviously different ways to write the same argument, and you might find this more compelling. I don't know. Do you guys find this nice? That one nice? You don't have to side with the professor. But I do think it's sort of, yeah, like I like this. Okay, so that proves the inductive assumption, or the inductive step, sorry. And so, so just to finish it off, it's like, therefore by induction, just to state the end of the proof, it's like, so that's true. So by induction, n factorial is greater than 2 to the n for all n greater than before. See, for some reason, when I write these proofs, I don't often explicitly say the P of n, but it's actually probably a good habit to just makes it a little more formalized. It's not really about like this. Yeah, I mean, you're right. These are the kind of things that I could have asked you to prove this on a homework or something, but when you're, we're doing the axiomatic number theory thing. That's stuff that's like, we're proving stuff that's kind of like obvious. And so later on, when you're doing math, you don't have to like prove. You can just appeal to like numerical facts that you know, with the understanding that you could always go back to axioms and try to prove those if you had to. But yeah, you don't have to really prove this. That's a good thing to prove. Maybe I'll put this on the midterm. Okay, any questions about that? Induction starting to sort of make sense? Yeah, notice, I mean, we have to use the inductive step somewhere, right? Like, or the inductive assumption somewhere. Like here, at this point, we used it right there. Up there, we certainly used it. I even said it explicitly by the inductive assumption. Okay. Let me go to the class meeting page. Share screen, turn the screen back on for you guys. Yeah, so I just sort of typed some of this stuff up. But okay, so group work. Here's fun group work. So this is another famous one that basically if you add up the numbers 1 through n, there's a formula for that. And then there's this thing called, have anybody seen the Tower of Hanoi puzzle? There's a website. Actually, the problem is most of the websites that you can, interactive websites, give it away, what I want you to do, which is basically see like a strategy for solving it in a nice number of moves. Like what's the minimal number of moves you can solve it in. This is the Tower of Hanoi. Let's do it for level 3. Have you ever seen this? So the idea is like you want to move these 3 disks over to here, but you can never put a bigger disk on top of a smaller disk. I actually saw this on an episode of Survivor once. I watched like one random season of Survivor, and then the puzzle was like the Tower of Hanoi, and I was like, oh, I would last 2 seconds on Survivor, but I was like, oh, I could solve that. How do I start? So I want to end up with the 3 disks here, but I can use this too. There's like, a lot of times it shows like 3 pegs that you can put the disks on. There's actually physical versions of this game too, but so I can move like here, or I can move there. That was inefficient. Right? So I want to end up with these 3 disks here. Where should I put this one? Here? No, here? Okay. There's not many places this can go. There. Here? No. Okay. So you get the idea. So you move that there, and then I need to move this out of the way. Okay, so 7 moves. Ooh, for doing this with 7 moves for 3 disks, but I guess I want you guys to try it for some different numbers of disks. I mean, there's also 1 disk. Woo! 2 disks. That was 3 moves. Okay, so then I guess the question is like, if you kind of use this good strategy, what's like, you can solve it in at least and at most this number of moves. And that's what you want to prove by induction. So the idea is first to try to figure out what the number of moves is, and then to try to prove it by induction. It's kind of fun. You can use this link if you want. I Googled like Tower of Hanoi interactive. Then the problem is a lot of them tell you the target number of moves, which gives it away. So I had to pick one that didn't. So, all right, and then there's a couple other problems that are interesting. So you guys want to do group work? I feel the excitement. Groups, do we do the same group? Do you guys remember? Should we can you guys put yourselves into groups? I can do it for you if you really want. All right, so yeah, try to do, the first one is similar to the first proof that we did. So I just want you to try to do that. And then the second one is more fun to play with. All right. Oh, and I'll pause the recording.